First of all, thank you very much, sir, for accepting the invitation. This is a AICT fund sponsor, particularly FDP. They have new platform called ATAL's, AICT's Learning and Teaching Academy. So under through that platform, we are arranging this 5 days, you can say FDP on advances in computational fluid dynamics. So thank you very much, sir.
Thank you.
And I would like to introduce formally Dr. Sandip Saha, sir. Sir is an associate professor in the Mechanical Engineering Department, IIT Bombay. Sir has completed his BE degree from Jadavpur University and his MSc and PhD from ISC Bangalore. Prior to joining IIT Bombay, sir is associated with many organizations like Tata Steel. Sir has already completed his postdoc from University of Leuven. Is the pronunciation correct, sir?
KU Leuven.
Leuven. Okay, Leuven.
Leuven, yeah.
Belgium.
Belgium, yeah.
Sir has received the base fellowship to conduct research on solar thermal application in USA. His research interest includes computational fluid dynamics, heat transfer, thermal management of electronics, microchannel cooling, thermal storage system for solar thermal applications, and thermal management of buildings. So he have a lot of publications that I don't have to say about, sir. So you can just go to the Google Scholar and just check it out. Sir, thank you very much for accepting the invitation.
Thank you very much for nice introduction.
Yes, sir. Yes, sir. Yes, sir. Sir, over to you, sir. Now you can start the session, please, sir.
Thank you. So today I will present one topic on CFD, which is mostly the application of CFD. This is on latent heat problem. So this is broadly means you can actually apply to any type of phase change from solid to liquid or solid to solid. So here I will not cover any phase change from liquid to vapor or to from solid to vapor. Okay, so here the comments I will present a generalized concept where we will see that how to model latent heat problem where change of phase is from solid to liquid or solid to solid. Okay, so here I will discuss broadly about different modeling techniques and as well as the fundamental, the basic CFD models which are used to actually analyze this phase change problem for say latent heat of thermal storage or for any type of storage. Okay, so here maybe I'll not very much going into the discretization of this equation. Rather, I will try to give you the flavor that how to actually develop a model for a given application. Then once you have this type of equations, okay, then you can obviously use either finite volume method, finite element method or finite difference method. This is your choice to actually discretize the equation and run the problem. Now, obviously, whatever the equations I will demonstrate, either you may find those equations in the commercial software, or maybe you can write your own code either in Fortran or C or even MATLAB also. So it's basically a fundamental modeling approach for analyzing this latent heat problem, specifically solid to liquid phase change. So here I will take the example of phase change material and then I will go to the modeling approach. Okay, so first, this problem was analyzed by Stefan in 1890. So it is not a very new subject. This is a very old subject, and from there this problem started by Stefan, and he analyzed actually the ice water melting actually. Okay, now first of all, we need to understand that why I need to go through this modeling, as this modeling is existing for more than a century, you can say now. Okay, and what is new thing is coming now. What I'm saying is that if you open even papers that any journals, okay, some energy journals, even heat transfer journals, you will see till today publications on this phase change problem are huge in number. Okay, so you understand that that means there are very much significant importance are there in this problem, although it is a century old problem. So why that I will tell you gradually, that what are the scope of implementation or improvement and scope of the application for in different cases, engineering fields basically. Okay, so I will show you one video. You will realize that what we can do actually. So it is showing that how ice is melting at the North Pole with time. Okay, now here obviously this is taken from NASA website, where they are trying to predict, or they are already captured this thing, that they are trying to say that how ice is melting. Now if you want to predict that how much ice will be left after certain years in future, then what you have to do then you have to do some analysis basically. So that analysis is basically a phase change analysis. Now this type of analysis what Stefan actually made, okay, during 1890. So that's basically a analytical type of analysis, which I will go through briefly at the beginning, so that you can understand the essence of numerical model. And that's why this type of problem is called Stefan problem, as this problem is associated with him who actually initiated this problem. So now going into the problem, let us first understand that what happens. So here phase change material I have denoted. It is basically a material, any material you can choose, which actually changes phase from one state to another, from solid to liquid or liquid to solid. Okay, or solid to solid is also possible in for some material also, where they just change the crystalline structure. Okay, so here phase change material means you can term ice as also phase change material. You can term the paraffin also as phase change material. So whatever the common materials you see in daily life can be termed as phase change material. Okay, so that's why. And this concept is not new to us. It is, maybe we have learned this concept during our schools. Okay, so what is that? That if you take one substance and if you heat it, let's for example, if you take ice and if you heat it, what will happen? The temperature of the ice will go up, and when it reaches its melting temperature, it will start melting. And during that phase, if it is a pure material, then temperature of melting will be at constant temperature, or melting will occur isothermally basically. And once the melting will complete, then again temperature of the, now it is water, will rise. Okay, so when the temperature of the ice as well as temperature of the water increase, so during that time the heat absorbed by ice or water will be in the form of sensible heat, whereas during melting the absorption of heat will be in the form of latent heat. So that means when I will use this type of material, my prime concern is two things. One is melting temperature according to the application where I will use this material. Second one is the latent heat, because I am only utilizing latent heat in my application, not the sensible heat. So here I will not talk about any sensible heat material, because it is obviously depends on the heat content depends on MCP delta T, which is not very much useful to us, whereas we are actually concentrating on the latent heat part. This we should understand. So if we understand this part, that okay, we are only utilizing latent heat, that means that if the material is melted, okay, or if the ice is melted, then for the application there will be no use of this material, because when the material melts, it will go into the sensible heat range. Okay, so there you don't use this material. So that means you have to solidify this material back to its original condition, means original state, means in solid state. Then again you can utilize it. So that means the application, whatever I will choose, it will be a cyclic type of application, means heating or melting and solidification. Again, melting and solidification, like that we'll always use. So I will not use this thing for a continuous operation. Okay. So mostly, if you see in real life, most of the applications are cyclic in nature. Take it as solar radiation, it is cyclic in nature. If you also run, say, your laptop, also your desktop, that is also cyclic in nature. But if you are running, say, cluster, that's not a very cyclic in nature, okay, because that is running for many days and maybe years, okay. There is server basically. So there, PCM-based cooling technique may not be useful in that sense, but you can apply this material also in those cases where there is some base load cooling system and you are using this type of material for taking care of peak load thermal management. So then you can easily see that it's a cyclic type of operation. So what are the different type of applications? It could be spacecraft, avionics, thermal control, portable communication equipment, laptop computers, wearable computers, power electronic equipment, casting and welding. In energy also you can use it. Okay, so there are various types of applications. Now we'll first understand the one-dimensional problem and try to figure out that what the problem is there. Okay, let us first see what the one-dimensional problem, what Stefan actually solved. Okay, so what is there that he considered, or the material is considered to be in solid state, or it is changing phase basically from solid to liquid. Okay, take it like that. So solid is there, liquid is there, and in between there is a sharp interface, okay, which is called melt front. So during melting or solidification, as the material solidify or liquidify, or maybe melts basically, the melt front accordingly progresses or recedes. Okay. Now whatever the situation be, you can write governed equations for solid state and liquid state. So for solid, obviously the simple energy equation can be written. It is del square T by del X square equal to 1 by alpha del T by del T. Okay. Similarly for liquid state also you can write. Now at interface, you have to balance the heat flux. So what is the heat flux is coming from the solid and it is going to the liquid, has to be balanced by the movement in the melt front basically. So this is that Stefan condition or interface condition I have written at the middle, where the left hand side is showing the heat flux coming from the solid, then minus heat flux that is going to the liquid, which is balanced by the movement of this melt front basically. Okay, now this is the, if you just plot the heat flux, but basically this is the latent heat of fusion. Basically you are plotting with temperature. You can obviously see for pure material, when temperature is basically constant, then you have this increase in latent heat basically, or energy content basically. So this figure is showing that. Now how to solve this equation? There are many ways you can solve this equation. One way is that you can assume this material as semi-infinite medium material, and you can apply that equations and solve the problem. Another way you can solve is that you can use some integral method to solve this problem also. But Stefan used that semi infinite medium approach and solve this problem. So if you use that semi-infinite medium approach, then you can find the temperature distribution in liquid phase, then temperature distribution in solid phase, and also you can write the equation for interface movement. Now this type of equation where both that movement term and that term xa or lambda, here it is written, okay, which is actually non-dimensionalized form, okay. So if it is exist on the both sides of the equation, then it is called transcendental type of equation. So solving this equation is not very easy, but nowadays MATLAB and other type of software is there, which if you just go a little bit code it, it is very easy to solve. So this way you will get it through some numerical solution. But earlier days when there was no computers, then people used to approximate these solutions using some type of method like Newton method, and they come up with some explicit type of form of melt front movement, which is given by this equation. Okay, so once you have these three equations, you can easily calculate the temperature distribution in solid region, temperature distribution in liquid region, and the melt front movement. So here, from till now, whatever I told through the new analytical model, you have now, I can actually conclude few things that, okay, I can find the liquid and solid temperature, but here I need to track the melt front explicitly because we are calculating the melt front movement explicitly. Now, if I try to implement this thing in numerical model, that means if I have to track the melt front, then I have to devise my grid in such a way that my grid actually moves along with this interface, okay, to capture it. Otherwise, I cannot capture. So that means I need to construct moving grid instead of stationary grid. Okay. Now, moving grid means what velocity it will go or what speed it will move. It will move at the speed of the melt front movement. So every time you have to keep many, you have to actually, you have to store many parameters, or you have to use you have to do many bookkeeping to actually get the bookkeeping to store the information of grid, basically. Okay. So that means I have very much problem. Okay. In that case, another problem is that the solutions only exist for few simple problems. Okay. And if the domain size is 2-dimensional, then you may not be able to use it semi-infinite model, then it will be very difficult. So that's why we have to shift to numerical analysis. Okay. And once we have the equations, and then we can use finite difference method, finite element method, or finite volume method to discretize those equations and solve the problem. Okay. But before that, what is the modeling approach? Now I will start describing. Now, as I told you just now, there are not one type I just told you, that moving grid approach, where you are explicitly tracking the melt front and you are then calculating the solid and liquid phase temperature. And the problem is you have very high amount of bookkeeping. Now, if I want to employ fixed grid method, then the advantage will come that I need not to keep many parameters for many. I need not to store many parameters associated with the moving grid. Okay, so that is one advantage, and my computational time will be less doing so. So now, if we do it, then the problem arises is that I cannot track the melt front explicitly. Okay, so that means in case of fixed grid method, the melt front will be tracked implicitly. Okay, so implicitly means I will, the concept is like this, I will actually calculate not the temperature here, I will calculate the enthalpy, okay, in the domain, and I will try to see the enthalpy which actually is in the range between 0 and latent heat, that range I will say that it's a male front. Okay, so this male front now, it may not be a sharp male front. Okay, it will be a diffuse type of male front. Okay, so diffuse over few numbers of control volume. So normally when I mean for pure material, I haven't shown exactly that simulation, but normally what happens when you simulate using these methods, then for pure material, one control volume thickness will be the male front thickness, which is not the actual case in real real situation. It should be a sharp one. But as you know, the numerical analysis cannot handle the sharp discontinuity. So basically, over that small range, it is actually changing parameters such as velocity, such as enthalpy from zero value to some finite value. Okay. Now, under fish grid method, there are the various kinds of methods. One is enthalpy porosity technique. Another one is apparent heat capacity method. Third one is temperature transformation model. Okay. So now these models actually means equation we write for single domain approach. What is single domain approach? That we will write equation for only a single domain. Means it could be either solid, it could be either liquid, or it could be both solid and liquid. That means when I write one equation, or when I solve the one equation for two different type of state, which is solid or liquid, that means I should have some type of switching function inside this type of model, which actually switch the velocity from 0 in solid to some finite value in liquid. Okay, so that means there are some type of device should be there in this type of technique which will take care of this. So I will now demonstrate how this is done in this type of model. So apart from enthalpy porosity technique and in apparent heat capacity method and temperature transforming model, there are other models also like phase fill method, level set method, volume of fluid method. Okay, where you use multi-domain approach. Okay, means you write the equation for solid phase and liquid phase, and also write equation for the male front also, which is in the form of advection type of equation actually for level set and volume of fluid, and you solve those equations, and then depending on the type of method you detect the interface. Now in case mostly this level set method, volume of fluid method, whatever you employ, it will again give you diffuse type of interface. Means it has certain amount of thickness. However, nowadays level set method is coming, new type of level set problem method is coming, where they use sharp level set interface method. Okay, where they can predict a sharp interface instead of diffuse. But again, that's not our main objective here. In this talk, I will be considering the fixed grid method for enthalpy porosity technique, apparent heat capacity method, and temperature transformation model for phase change problem. And also I will consider the material as a pure material. That means melting will occur at a constant temperature. Okay. And now apart from this method, there are many more methods, that meshless methods, lattice-Boltzmann method, which I will cover briefly again. Okay, to give you a highlight that how these methods work. Okay, normally volume of fluid method we don't employ in this type of phase change. Rather, we employ in those cases where free surfaces is to be detected. Okay, like air, means that interface of air and solid liquid, basically, where liquid is rising and you are pouring the liquid and liquid is rising in a container and air is displacing, basically. Okay, because liquid is displacing air and you are trying to figure out what is the interface between air and liquid. So there we normally use volume of fluid method. So here we don't use much. Okay, whereas level set method, people have now started to means developing that type of means trying to incorporate this method in this type of this problem, but that is still in developmental stage, I should say. Okay, so most famous methods are the top 3 methods which I will discuss now. Even lattice-Boltzmann method also people have done basically. Okay. So now concept on phase change modeling. First, what I will do is that first I will now show you how the models are developed. Okay, the fundamental models are developed. Then I will show you their application. Then I will show you that for different types of problem, how this model will be implemented. Okay, so now let us first take that enthalpy method. Okay, an enthalpy porosity method. Porosity will come a little bit later, because when we incorporate this momentum equation, then porosity term will come. Otherwise, enthalpy method is known as, okay, enthalpy method, as you know, that it is dealing with the enthalpy, not the temperature. Okay, that means when I will write the energy equation, I will write the energy equation not in the terms of temperature, but in the terms of enthalpy. Okay, so what is the definition of enthalpy? Enthalpy definition is basically C into T, means specific heat into temperature. So obviously that means where whatever the energy equation you write, the means rho Cp del T by del T equal to K del square T by del x square. The left hand side you will always see that rho C, if you put inside that del T, it will always give you del rho H. Okay, you can easily convert into H. Okay, left hand side. But right hand side you cannot convert to the H unless you divide it by the Cp basically. Then you will get it. Okay. So normally left hand side is always converted to H. Now such, if you convert that equation into this the form what I just mentioned verbally, so this will be look like in this form whatever I show you. Okay, so now we have further actually non-dimensionalize it to make it little bit look it classy one, but normally it is basically rho del rho H by del T equal to K del square theta by del x square. This is one dimensional model I am first showing, because if you understand this, then it can be easily extended to 3 dimension. So now here these parameters are taken as non-dimensionalized form to as a non-dimensionalized parameter, which will give you this equation. Okay, now once you have this equation, and now here if you discretize this equation using say finite volume method or finite difference method, you will be getting simple this type of equation where phi I at new time state is related with this old time state and the neighboring grid points. Okay, this is very well known and very easy to derive the equations. Okay, now this phi actually, please remember, this phi actually denotes actually enthalpy. Here H is the enthalpy, which is nothing but C into T, CPT basically. Whereas theta in this case is a non-dimensionalized temperature, and it is, if you see the definition wise, here lambda is basically the latent heat. Please remember, okay, because later on this sign will change to L. Okay, so initially this will be lambda, which this definition actually is Stefan definition, Stefan number definition. Okay, but here it is mentioned as non-dimensionalized temperature. So here temperature is there, that's why. Okay, now how you can actually set this condition? Now you know that when temperature is less than the melting temperature, if you go to this equation of state, then it is very much clear. Then when the temperature of solid is less, or temperature of the material is less than the melting temperature, then it is in solid state. Okay, so then what will happen is that then the enthalpy basically, the definition wise in this case, is theta is equal to phi, because you obviously see that T is less than T melt, so this T melt and THS will actually vanish in the solid state. Okay, so there theta is just equal to phi. Okay, so similarly if you follow this logic, then you will see that during melting T is equal to Tm, because I am assuming that material as pure material where the melting is going on isothermally. So then this theta will be 0, then that means phi theta is basically 0 during that melting. So that means when the phase change is there, when latent heat changes value from 0 to 1, say, because this is non-dimensionalized value, so then theta is 0. And similarly in liquid phase, if you just do that small calculation, that H equal to CPTM plus the latent heat specific heat content during liquid phase, okay, or during liquid or in the liquid, then you can easily get this value, the theta equal to phi minus 1. Now this is one-dimensional problem and very easy to solve. Okay, you can actually solve this problem by hand, okay, by pen and page, okay. And for if you just draw 3-4 grids in your rough paper or notebook, you can easily solve it by hand, okay, without going into any type of numerical scheme. Okay, if you have this algebraic equation, you can easily solve, and I will always encourage you to solve this problem. Okay, then you will very much easily and you will very much comfortable with these methods. Okay, if you have this fundamental understanding. Okay, once you solve this equation, now if you plot the say Miltron movement with time, okay, what will happen is that you will get this type of wavy type of graph. Okay, now exact solution whatever you will get, that also looks like a wavy, but it's not very much wavy, because exact is continuous over the domain. Obviously, you know, analytical solution is continuous over the domain, whereas in case of finite difference, finite volume or finite element, you are discretizing whole domain into small parts. Okay, so that means you are getting a discretized solution at different nodes. Okay, so that means I am getting waviness which is actually of the length of, if you calculate, of the length of delta x, okay, or the grid size. Now why it is happening? Because so what it is doing, this simple model is that when the phase change is occurring in a node basically, or in a control volume, so it is keeping the temperature at constant value unless the phase changes occur, unless basically the latent heat content changes from 0 to its full value basically. Okay, till that point it is keeping the temperature same. So that's why you are getting a flat type of curve at the end, okay, towards the end of this process, okay, in that control volume. Okay, so this can be removed if you refine the grid, or if you use some type of actually advanced model. Okay, advanced model means if you use some different type of solvers. Here as I told you, the solvers are very simple. Here solver is very simple. You have only use hand and just use your calculator to find the thing. Okay, now to remove this wavy type of solution, you can actually refine the grid, or you can advance your model. Means you incorporate different type of solver part. So here through analytical, through this simple model, I will not show anything. If you are interested, you can actually use diagonal matrix algorithm. This maybe you have, you know it, and if you implement that algorithm in the solution, in the solver basically part, you will actually not get this type of thing. Okay, so you have to little bit refine the grid and use the TDM. You will get the good perfect smooth curve, more or less. Okay. Now, I will not go into that. Rather, I will show you how this model is further improved. Okay, that so although I have named it as advanced enthalpy technique, but it's not like that. Why I have termed it? Because here the enthalpy part is splitted, okay, into two parts. Okay, that's why I have named it advanced enthalpy technique. So the concept here is that, okay, whatever rho h, what I just told you in my previous slide, that h part is now splitted into two parts. One is the entropy sensible heat content, another one is latent heat content. So h plus delta h. So now if you substitute h plus delta h value in place of capital H in this equation, then you will see that you will get this equation, rho delta rho h by delta t equal to this divergence of k grad of t minus del rho delta h by delta t. Now here you understand the right hand side with minus sign, that term is basically a source term, okay, which actually takes care of the phase change behavior. Okay, either it could be from solid to liquid or liquid to solid. Okay, now what is the definition of delta H? Delta H is that if temperature of the material is below the solidus temperature, it is just to generalize it, means if there is a range of melting temperature, then you know solidus temperature and liquidus temperature. So if the temperature of the material is below the solidus temperature, then latent heat content will be 0. And if within that solidus and liquidus temperature, the latent heat content within that control volume will be governed by the liquid fraction, how much liquid is there, into the latent heat content. Okay, and if the temperature of the domain is higher than the liquidus temperature, then obviously the latent heat content will be full, that L. Okay, now here I understood this definition delta H, but here you understand that either that means I have to calculate FL, means liquid fraction, how it is varying with time, temperature, or how it is varying with time, whatever it could be. Okay, or I have to know delta H so that I know FL. So either of the things you need to know. So that means I need to formulate delta H in such a way, or I need to have some equation of delta H in such a way that I can find that with temperature, how delta H is changing. Okay. Now, the derivation of this equation, I didn't show you here. Okay, so if you are interested, so you can go through some literature, there it is given. But broadly, what is done, let me tell you, is that this equation again, this del rho h by del t equal to the diffusion term and then the source term. So this is again discretized and then again rearrange. It's not a very difficult to derive this right hand side expression. Okay, that enthalpy update content. Okay, then you will see that delta H can be actually written in terms of the delta H at old time step with this value. So here lambda actually denotes, please note the relaxation factor, because now you are now solving the equation implicitly. Okay, not the explicitly, what we are doing earlier. So implicitly, if you solve, that means either you are using Gauss-Seidel method, okay, or some other iterative equations or method to solve this problem. So there you know that we need to use some relaxation factor. So just to remove the instability in the solution, basically. Okay. So now this TPN. In case of this is basically the grid point temperature, and Tm is the melting point temperature of pure PCM. Now from here also, if the material is impure, you can actually write this expression in terms of solidus and liquidus, which again is not a very difficult to solve. But as I am concentrating only on pure material, because if you understand pure material, it is very easy to understand the impure case where you know the solidus and liquidus temperature. Okay, so here this enthalpy updation scheme, if you use, then you will find that you know now this source term at the source term during the iteration, you can easily now calculate everything. So this is easy to code and people use it for now simulating phase change, where the assumption is that conduction transfer is occurring, because I haven't included any convection part here or advection part here, say rather. Now the value of the relaxation factor is given as 0.6, something like that. Okay, and this is we don't change. Okay, obviously, but if you change it, you will see that the solution will not change much. But normally we take 0.6 value for this case. Now this is simply the repetition of that how H is varying with temperature. So as you know, during phase change, the temperature, that enthalpy at that melting temperature will change from 0 to a high value. So it is depicted here. Okay, whatever the condition I showed earlier, delta H condition, it is written there. Now, this was the fundamental of the enthalpy method. Okay. Now I want to generalize this model. Okay. What generalization? I want to introduce fluid flow. I want to now incorporate many other things. Okay. Means you can also incorporate natural convection, anything you can say you can do it. So now for that, my assumptions are the fluid flow in the liquid region is Newtonian. It is also laminar and incompressible. Normally, all the fluid flow in case of phase change is laminar. Okay, so it is not very vigorously heating. Okay, and here for this case, I am assuming local thermodynamic equilibrium exists. I will later on will show you that if LTE means local thermodynamic equilibrium does not exist, then how I have to handle the situation. Okay, there are certain cases I will tell you. Okay, now also thermophysical properties right now I will not vary much. Okay, it is constant. And volume change of PCM during melting and solidification is neglected. Okay, so there is no shrinkage and expansion during solidification and melting. But in the last of my talk, I will tell you that how to model these things. Okay, now the continuity equation, it is written as it is, where del x means del u by del x equal to 0. Momentum equation, obviously this Navier-Stokes equation. Only you see that there is some source term introduced, SI in the momentum equation, and energy equation was as it is, only I have introduced one advection equation term basically in middle on the right left hand side. Okay, now here you see that these equations are valid for over the domain, means if the domain could be solid, domain could be liquid, or domain could be either solid and liquid. So that means the momentum equation means when you solve actually solid phase, okay, has to be vanished, okay, by default, because there is no velocity. So that means I have to take care, means I have to use some type of switching function which will set velocity in solid region as 0 and liquid velocity, liquid some finite velocity in liquid region as finite. Okay, some value. Okay, so that is the switching function, and SH is nothing but which I derived. Okay, so for energy equation I don't have any issue. Okay, this I have already derived. Only I have added advection term to taken care of convection. Whereas in melt momentum equation there is some source term, and also I have burden that how to model actually the phase change as well as how to set the solid velocity as 0 basically. This is intuitional. So this is called velocity correction methods now. Now what are the methods available? There are 3 types of methods available. One is switch off method, second is source term method, third one is variable viscosity method. So here I will discuss the source term method, where the source term Si, which is actually in 3-dimensional coordinate S1, S2, S3, is written in this form A into U. What is A definition? A is written as minus C into 1 minus FL to the power Q divided by FLQ plus B. So FL is liquid fraction again. Okay, please remember. Now C is the, what is the value of C? C is the morphological constant. Okay, what is morphological constant? This is the constant which we choose during the phase change of a particular material. It depends on the material actually. Okay, and also the process. I will show you if you change this value, what will be the effect. Okay, by default, we usually take 1.6 into 10 to the power 6 value, but this can be changed to any value. I will show you. That is next slide I will show you. But for the time being, you understand that A is modeled in this fashion. And why A is modeled as minus C 1 minus FL to the power Q? This is actually replicating the porous medium model. So you are assuming the melt front, which is actually diffuse one from say velocity from 0 to some finite value. Okay, so that your melt front you are modeling as a diffuse material, porous medium material, where the pressure drop is actually replicating the pressure drop expression given by Karman-Kozlowski equation. Okay, there are actually, if you see, remember the porous medium model, we know that Darcy equation, then Darcy actually gave some pressure drop expression. But if you use Darcy equation here, you have a difficulty because you will have more unknowns. Okay, so that's why people don't take that. They use carbon cogency equation where the pressure drop can be function of the porosity directly. So porosity here is replicated by the liquid fraction basically. Okay, so there is no new thing. There is nothing new thing, means it's a logical way they people actually model the thing. So now here one catch is there, some B is added at the denominator. What is B? B is basically the value which is taken as 0.001. Now if you see FL if equal to 0, say if B is not there, just FL equal to 0, then you see A will be undefined, and in numerical model there is no undefined term. Okay, then people model will not work. So that's why people add one B value, small value, which actually means if FL equal to 0, it will not, code will not will not stuck basically. That's why they add B. Okay. Now if you see, now if it is in solid phase, understand here, then what will be the value of A? So value of A will be something in the order of 10 to the power 11, because B value I have taken as 0.001. So 10 in the order of 10 to the power 11. Now if you just substitute that value here in SI and just divide it here, means if you take the left hand side, then you will see whole momentum equation will vanish with that, because you are dividing momentum equation by 1 by 10 to the power 11, which is more or less 0. That's how the switching function works. Okay, no, sorry, source term works. Now this is for phase change material based, means only phase change material is kept in the container, say. So how in phase change material, how you will switch on and switch off the velocity in solid region and switch on the velocity in liquid region. But say if phase change material also contains some type of solid material like film or like some capsule, okay, then what you will do, then there also you have to switch, means you have to use, means you have to switch off the velocity, means velocity has to set to 0 in that solid region also, in film region also. Then we employ also the variable viscosity method. So if you see also here, if you set mu as very high value for solid region, then also you'll see this momentum equation will also valid. So these are the two techniques mainly we employ to actually set velocity in solid region 0. So this method, this source term method, we employ for melt front, where we set the velocity 0 in the solid region. Whereas when we go to the solid material in the phase change material, say solid material present in this phase change material, then we employ this variable viscosity method. Okay, so I hope it is clear. So now this is the algorithm of this equation. So basically you have to start initialize TUV, you assume something, then as it is a transient equation, so you have to set the T means you have to store the values at T old, then you advance the time step, then you calculate the source term, because it should be known by default in CFD. Then you solve UVT according to the say simple algorithm. Okay, then if convergence is there, then okay, very good. Otherwise you have to update the nodal latent heat value, and then you have to reiterate basically. Okay, so this is my personal experience, that solving the problem and solving the equation using this algorithm and using the value of t equal to 0.1, okay, you will get the convergence in the solution. But the problem means the solution may not converge when there is a phase change from solid to liquid, means at that juncture, okay, the initiation of melting. So there you have to little bit careful to set t time basically, because you have time also in your hand to converge the solution. So there you may not be able to use 0.1 second for solution, rather you have to use like 0.01 second to during that time, only during the initiation of the melting. Okay, if it is if you are done, then whole simulation, this whole melting process will be good. Otherwise you will have some trouble at the beginning of the melting process. Now as I told you that C has some role, So recently people have shown that if you change the value of C, it will change. But normally again, it is normally taken, and if you see here also the experiment they have done. So normally that value is something like in the order of the order of 10 to the power 6. Normally we take 1.6 into 10 to the power 6 value. But this paper showed that how this model, how the value of C changes, then how it is affecting the male fraction, this shows. But again, it is confirmed that that value, whatever we take, like 1.6 into the power 6, it is good. But in fluent, it is 10 to the 5. So sometimes we use 10 to the 5, sometimes we use 10 to the 6. But please remember, you have to validate your code always before running anything. So validate your code with some experiments, basically. So this is also done in that way. Okay. So some example I have taken. So validation I have taken. All what I will do, I'll show you the model and the validation, so that you get the confidence that okay, model is working. If validation is not there, then the model nobody will believe whatever you are developing. Okay. So this is basically side heated tall enclosure with aspect ratio 10, and PCM is inside. So tri-octa 10 they have used, and they have used numerical model as well as experimental model. So they have used, seen the male front movement. So dark region is liquid, and solid region and bright region is solid, basically. So this is the progress of male front, or say progress of melting with time, which they have shown validated through this numerical model. So it shows fairly good validation. Okay, this was the first paper, actually first few papers which came during say 2002 or 2001. Okay, to actually validate this type of models. Okay, then this whatever I told you till now are all enthalpy porosity method. Why porosity now? I hope you understood. Porosity is because you have modeled male front as a porous medium. That's why the porosity came. Otherwise, enthalpy was there. Now porosity only came because you have modeled your problem that model the male front as a porous medium. Now next one is apparent heat capacity method. So what the fundamental basic is that here they change the specific heat during the melting. So change the specific heat how? So basically, if you see the dimension of latent heat, it is basically kilojoule per kg. Whereas CP, if you see in specific heat dimension or unit, it is basically kilojoule per kg Kelvin. So some Kelvin has to be divided. So then you will actually get the latent. If you divide L by latent heat by some delta T or temperature, then you will get the unit same as the specific heat unit. Okay, so that is the concept basically. So their concept is when melting will start, when the temperature of the domain will reach the melt temperature, then you will now model latent heat as some sort of sensible heat, basically. But how it will be modeled? So if you see this thing, CPSL plus L by TL minus TS. Okay, so TL here is T liquidus, TS is T solidus. Now, if the material is changing phase over a range of temperature, then this method is very good because there is well-defined TL and well-defined TS. However, if it is a pure material, then setting up of TL and TS can be possible if you are validating your code. Then you have to determine what is the value of delta T for which the code is working, means giving the same result. Okay, if there is no hard and fast rule for this delta T. You can set as 0.1, you can set as 0.01 also, you can set as 1 also. So it has to be validated. So that means apparent heat capacity method is little bit, I will hesitate basically to apply for a pure material. Whereas in case of enthalpy porosity technique, it is very good because the expression content itself is a single melting temperature. Okay, so that's why I will be using. But where is the advantage of this apparent heat capacity method? It has advantage, two types of advantage. One is computationally inexpensive. Okay, because you have to only change the specific heat. Okay, and it is done explicitly. And second one is that if the melting is occurring over a wide range of temperature, then apparent heat capacity method is very good. okay, because it is computationally less expensive, as well as implementation is very easy. Whereas in case of enthalpy porosity method, pure material, it is implementation is good, but for impure material, I have to do some more extra work in that code to get the result, okay, because I need to update, change the enthalpy update scheme, okay. But again, that's a very rigorous method, and it will take some more time to solve the problem. So this is the little bit difference between these two problems, these two models. Okay, now third model is there, which is called temperature transformation model. So mainly it has been seen that there are some stability issues as well as convergence issues associated with these two methods. Okay, if you are not setting the time step value and delta x value within some range, okay, because that is a little bit trial and error method to find that range basically for a given applications. Okay, so in order to get rid of that, they defined now this instead of CT, they define C prime C0T in this fashion, which is, if you see, more or less is in the form of the apparent heat capacity method. But here they actually also set that thermal conductivity, which is in this form, okay, which is not there in case of the apparent heat capacity method. So in this way, they also developed the temperature transforming model. But the popular models, whatever I described, are the first two models. If you open any phase change material based modeling, you will get those values, those models easily. Okay. Now, next one is, I will just introduce this LBM model. Nowadays, it is used. So, the LBM model, that Boltzmann equation, generalized form of the Boltzmann equation is written in this form, the top side. And here you have to find the distribution function for density and temperature. It is already given. Now, this is for generalized problem where there is no phase change. But if there is a phase change, then you have to model according, say, to the enthalpy porosity method. If you see really enthalpy method, okay, CT plus FL. Okay, so in that way, you incorporate the or you will change the function basically. You change the distribution function of the temperature. Okay, only then you solve it. Okay, and this method is more or less explicit method. You can get the result without employing any implicit scheme. Now, this is some validation where it shows that with melting also, after you do full melting, the Rayleigh-Bénard convection, if you simulate it using this scheme, in this method, it says very fairly good match with some analytical model as well as some numerical model also. Now, till now, whatever I was describing, all about fundamentals things, like how you will now model the phase change problem. Now I will show you some applications. Okay, now if you understood that, now next one is that how you can do it. Okay, for the latent heat thermal storage, this is one application I chose. Remember, whatever I will show you, more or less this is applicable to any other type of configuration, in the sense any other type of applications. Here I have taken only one, but here also various schemes, various configurations are there. That means there are various types of models available. So obviously you will see that when you go to other type of engineering applications, other type of field, not only in solar receiver, other type of like thermal management of fuel cell, thermal management of electronic devices, there also you will find similar type of configuration. So modeling will be same, only the configuration, the shape will be different. Okay, so here we are employing latent heat of fusion, latent heat of latent heat of thermal energy storage, because we want to remove the intermittence in the solar radiation, as well as we want to extend the electricity generation during the after the sunset basically. Okay, here I have given one example that 200 degrees centigrade, 137 degrees centigrade is the cycle. Okay, means during peak hours, means when solar radiation is available, 200 degrees centigrade will be achieved, and during, say, intermittency, when solar radiation during cloudy days is not there, then 137 will be achieved. This is just specification. Okay, now what are the different enhancer actually we use in phase change material? Okay, before going into this, let me tell you the problems of phase change material. So at the beginning of my talk, means in the second slide, I told you when the PCM, for PCM, how it works, that two points or two parameters are important. One is the melting temperatures is important. Second one is the latent heat is important. But apart from that, other things is also important, like thermal conductivity has to be very high, specific heat has to be very high, thermally inert, chemically inert. Also, it should be non-toxic, non-corrosive. Everything should be there. Okay, it's a perfect thing, perfect people actually. Okay, but again, nobody is perfect. So PCM is not also not perfect. So what is the imperfect in that? So PCM thermal conductivity is very low. It is in the range of 0.2, which is almost the same as the insulation thermal conductivity. Okay. Now, so how to improve the thermal conductivity? See, thermal conductivity is material property. We cannot actually change the material property in that way. So what we change? We actually change the overall thermal conductivity of the domain. Okay. So by introducing either fin or metal matrix, which is basically a structure of wear, or some other type of configuration, which is called encapsulated PCM. Okay. So there are three actually, if you see really, three configurations I am showing here. Okay, one is fin type, one is metal matrix type, one is encapsulation type. So apart from that, there are not much other type of thing. Okay, so whatever modeling I will present for these three cases, it is more or less you can use anywhere. Means it is more or less say means console, more or less a covered thing. Okay. Now first let us take the fin type. Here fin number of fins or fins are distinctive. Means it is present in the PCM and you can actually recognize it distinctly. So here that means I need not to think this fin plus PCM as some single fictitious material. So I can model fin as separate material and PCM as the separate material. So here that means, as I told you during my that enthalpy technique, enthalpy porosity, that introduction technique, here I can use single say energy equation, single entropy, a single momentum equation, single continuity equation for fin as well as the PCM. Okay, so here I have if I write the equation for this thing, same equation whatever I have derived, then this problem can be solved very easily. Okay, there is no new thing I have to introduce here. Okay, so here if I do, then I can show the efficacy of phase change material compared to the sensible heat, which actually shows that the outlet temperature of this from the storage of the HTF can be stabilized with the use of PCM. Here, the validation part I will show you later, where some experiment I will tell you. Here I have just shown you the advantage of phase change material over steel. Say, if I use instead of PCM, if I use steel here, what will be the advantage of PCM? Now, next one is the modeling approach for packed bed type of storage. Okay, so that one problem I discussed. Okay, which doesn't require any special treatment. What I actually already discussed. Now, this is another technique where modeling approach for packed bed storage. Packed bed storage means now PCMs can be filled in these capsules, in a hollow capsules, so steel capsules, any other capsules, and then this can be put into the container, and then you can flow the heat transfer fluid over it. HTF is heat transfer fluid. Okay. Now this can be modeled using two different methods broadly. One is single phase method, another is two equation method. Okay. Single phase model means you assume these balls or capsules and PCM as some single fictitious material. Okay, and then you model it as a porous medium. Okay, and second type of model is you can use two equation for either HTF, means for HTF and PCM, and within that there are several divisions. One is concentric dispersion model, another one is continuous solid phase model, another one is Schoeman's model, and Schoeman's model is the oldest model, okay, in this category. And what are the distinction? I can read it now, but if you see the equation, it is very much visible, okay, through the equations. So single phase model, let me first discuss. So in single phase model, what we do, as I told you, we just assume the material as fictitious material. Okay. Now here, let me tell you briefly first, before going into the single phase method, that we will still solve continuity equation, what I showed you. We will still solve momentum equation, what I showed you. But here is one catch, as I told you, that this equation will be, or this form will be solved using the porous medium approach, where we will assume that porosity phi is epsilon is the porosity of the material, okay, or of the container. So porosity means volume of void divided by total volume. So for metal matrix, means the porosity where epsilon will go, and where in this case epsilon will go for the encapsulated bed PCM, you have to little bit understand. Be careful about implementing the equation. So in case of metal matrix, the porosity is basically means the void means where? Void means actually means within the pores. Okay. So there are voids, and within that voids there are voids. Within that voids PCM seats. Okay. So here we voids PCM seats, whereas in case of this packed bed PCA, packed bed thermal storage, here the solids are PCM and voids are basically through which HTF is flowing, heat transfer fluid is flowing. So in one case, if you take epsilon in continuity equation, another case you have to take accordingly, means 1 minus epsilon in that way. That just that small difference. Okay, so you have to understand a little bit that one. Otherwise, the form of the equations are same. So continuity equation, this is for porous medium, momentum equation for porous medium. And for porous medium analysis, apart from the phase change source term, this SI, there will be one more source term for porous medium, because in porous medium, there is viscous resistance and inertial resistance that you have to model. So this is the viscous resistance, okay, minus mu k by k is the permeability, into ur is the velocity, and rho c by root over k in mod v, which is the inertial coefficient, okay, resistance basically, and the value of permeability, it is given, okay, it is known for different system. And what is the value of c, it is also known, given. It is not a specific heat, okay, it's a constant, okay. So here this rho GB, this is a Browsonic approximation. If there is some natural convection in this system, then we assume it. Okay. Now coming to that single phase model and two phase model. So now single phase model, as I told you, that you are assuming the PCM plus metal matrix or the HT, whatever, as the single fictitious material of having some effective properties. Okay. So then you use some equilibrium model. Okay, and then you write the effective rho Cp value using some volume averaging technique, whatever I've written. So you can use and also K effective using a volume averaging technique. So if you see, these are all linear function, whatever I showed. But here or means K effective plus K effective by Kp to the power 1/3. That expression is a non-linear term. So it depends on which type of system you are using, because many researchers have done some experiments on different type of configuration, and they have came up with different type of expression of K effective. Okay, it is readily available in the literature. Okay, so if you are not getting anything for a particular configuration, then you can obviously use very straightforward linear type of expression, which is based on the volume average. Okay, now if I use it and use it for this situation, I can actually solve the velocity field as well as the temperature field, isotherms. Okay, for different parameters. Now non-equilibrium energy equation, under which there are several models. Okay, so first model, let us, what are the non-equilibrium now? Now why, first of all, in equilibrium model, where it is there, and non-equilibrium model, where it is there, where you will use. I told you, no, in the beginning, the assumption local thermodynamic equilibrium exists. So here no local thermodynamic equilibrium exists. Why? Because if, remember this thing that if thermal conductivity of the PCM is much different from or significantly different from the thermal conductivity of HTF or the metal matrix, then there will be no thermal equilibrium between them. Why? This means that the temperature of the metal matrix will not be same as the temperature of the PCM, because the thermal conductivity of PCM is different compared to the thermal conductivity of metal matrix. Okay, so that's why you cannot use a fictitious material. Okay, now so then you have to use separate equation for HTF and separate equation for PCM. So in this case, I have neglected melt convection within the PCM, is there is no melting in the PCM. Okay, and also only the conduction is there within PCM. Okay, whereas in HTF, if you see, there is a convection and it is flowing, it is advective term is also there. Now how I can model now the source term here? If you see HTF and PCM, these two equations you have written for two media, but there should be some coupling parameters, coupling expression terms. So that what is the coupling term? That interfacial heat transfer coefficient is the coupling term. Okay, so that H normally for packed bed HSF is given in this form, which is given by Wakao. Okay, maybe in 1970s, and then but other than that, you see there is a source term which is actually taking care of the phase change in the PCM. Okay, so this way we model the non-equilibrium equation. Now you have seen the form. Now what is now concentric dispersion model and continuous solid phase model? So now variety will come now. So now when you will consider concentric dispersion model, so you see that the difference between concentric dispersion model and continuous solid phase model is that in concentric diffusion model, you are writing the expression for one dimension. You don't have any variation in the art direction, radial direction. Whereas in continuous solid phase model, you have a variation in art direction also. Okay. So if you have a variation in art direction, that means is that you can employ variable viscosity along radial direction. Remember that viscosity is not constant throughout the domain. Okay, it has been seen that viscosity, porosity, I made mistake. Porosity is not constant for entire domain. Okay, porosity actually varies with the radius. Okay, and at the wall, porosity means there will be more voids actually, because less particle will be packed there. Okay, please note this. Okay, now in case of concentric model, in order to bring the radial direction effect, they also solve the equation in spherical capsule. But here you see one thing, it means even spherical capsule can be placed anywhere at any radius basically. So whatever the expression you will get from spherical capsule, that can be placed at center or maybe at a distance of 1 mm, maybe at a distance of 2 mm, same value will get. So that means it does not take care of any radial distribution. Okay, in this case. Whereas continuous solid phase model that takes care. But in continuous solid phase model, the you cannot get the distribution in spherical capsule. That is one disadvantage. Okay. Now, having said that, you can actually write the equation in the generalized form, in this form, what I showed you. And this form you will get in a given, you will see in any book. Now, this can be, you can code it, or you can also write UDS, means user defined scalar, in ANSYS Fluent to solve this equation separately. And the method I told you, just have to code it in ANSYS Fluent, you can actually solve the problem. Okay, so this is one validation. It shows fairly good amount, good reasonable accuracy of this numerical model. Now, I told you that I have neglected melt movement in the PCM. Now, if I want to include that melt convection in the liquid PCM, Then what people have done, they have actually incorporated some effective value or effective thermal conductivity for taking care of the effect of convection. Now, if you see the convection, if you introduce, it will actually stabilize the temperature more compared to that situation where you don't take conduction in convection into the consideration. So male convection or the convection in the PCM is important. Okay, you have to take into consideration. Okay. Now, in case of metal matrix, we will also model this as porous medium. Only my parameter changes, the porosity definition changes and permeability definition changes. Okay. Now, this is basically validated with the numerical model. Here, if you see without metal matrix, what I was told, what I was telling you, this is validated here. Here, the difference is 0.5 degrees centigrade, whereas in case of two metal matrix, the variation is difference is 0.26 degrees centigrade. Now, why the difference is lower for metal matrix? Because if you see, if you introduce metal matrix, you are actually suppressing the convection, male convection. So it is more conduction dominant. Now, as these models are more conduction way of doing, some more conduction dominated problem means model. So that's why it is giving good accuracy for this case. Now, till now, whatever I discussed, whatever the models, these are all full-fledged models. Means it solves Navier-Stokes equation, it solves energy equation, it solves many other equations also. But to give you one example, that solving a domain of PCM which has a dimension of 42 into 42 into 25 mm, it takes around 72 hours to 108 hours to solve that problem in a normal computer. So if you for running only 3600 seconds, basically only running 1 hour. So you understand, if you want to run a system, if you want to test the dynamics of some thermal energy storage or some type of system for say 2 days 3 days of operation, then it will take long time to simulate. Okay, I mean, see, it may not be possible to simulate also, depending on the computational facility. So that means we need some reduced order model which will replicate, which will give you which will predict the phenomena with reasonable accuracy. So here I don't need very 1% or 2% accuracy. So here my accuracy is 5%. I am well good because I'm getting result within say 10 seconds or 30 seconds or just simulating one month basically. Okay, just to give you an example. So this is one kind of model now. So this is, I am showing you some multi-layered cascaded PCM where we are using different storage, different capsules in the storage to simulate it, to actually make it to actually change, to store the heat. So how we do the reduced order model? If you see this HTF and PCM equation, these are all semi-analytical type of equation or semi-differential equations, which is based on only the energy equation, energy balance basically. So how the HTF is exchanging heat with PCM and how this HTF is exchanging heat with the ambient, only that is written here. And some switching function is written FCZ, then epsilon Z. This is just to tell you that where from means which means where from this HTF is coming, means through the collector or through where is the inlet basically, or even where is the PCM also, means in which layer the PCM is also there, you can actually specify through this model also. How that FPZ actually is that switching function, that if you set that as 0, then it will vanish actually, means it will decouple. HTF and PCM will be decoupled. Okay, that equation. So using this expression, you can also incorporate radiation effect through the effective thermal conductivity model. So there are some BB model. I mean, there are some models actually available through which you have to just change the thermal conductivity. You can actually incorporate surface to surface radiation in this case also, surface to surface radiation model also. Okay, some validation we have done. So it shows fairly good result within 5% accuracy. So that means my model is working for different situations. Now, till now I told you whatever the thing is, that is for the without shrinkage. Now briefly I will tell the effect of shrinkage. So here, if you introduce shrinkage, that means my del, when that continuity equation del u by del x will not be equal to 0. So it will be actually equal to the difference between the mass, basically. Okay, so which is written here. Okay, so mass conservation equation is written in this form. Momentum equation will be as it is. Okay, but if you change the if you take the different properties of solid and liquid phase, then accordingly it will change. Okay, but note that I can cast my whole equation in in the known form. Okay, this is the known form, whatever I'm showing, plus is E. Now in AC, all the source term is is kept, which is explicitly known before the iteration, basically. Okay, so that means if I use this type of method and this type of formulation, then I can also take care of the shrinkage in the container. So some validation I am showing where rho s obviously is not equal to rho l. So here rho shrinkage is coming because of the change in difference. Okay, and some specific heat change, different change, everything is shown here. So some validation I'm showing that it is giving a good validation with the experiments. People have done experiments on this, and this is very recently developed model by us. Okay, so it shows very good agreement with the experiments. And also if we see another that was during melting, and this is during solidification, that also shows very good matching, okay, with the new experiments. And also if I see the shrinkage in a container, this is a verification, I should say, because remember, validation is with experiment, verification is with numerical model. So this San and Garimilla, they had done this model using Fluent, which we have done now with our shrinkage model, as well as generalized model, as well as we have implemented this in open form. So this is showing fairly good match with this result. Okay, so summary is that we have several models I have discussed for pure materials. Okay, now the models has to be chosen for a specific problem. Okay, what type of problem you are solving. But the phase change problem is always there, which is available. Okay, the model is always available, but you can improve that model also, like thermal temperature transformation model. Okay, that type of model you can also incorporate. So you show, in order to now find, you can always develop new type of model also to track the solid liquid interface. So this is up to you how you will now utilize this type of model to analyze the system. And when you start analyzing the system, you will understand the difficulty, then you will start developing the model. Okay, so hopefully I hope I stick to the within the time. Please tell me if you have any question. I will be very glad to answer those.
Yeah, thank you very much, sir. Thank you very much for the very nice session, actually. Is there any questions from participant, please?
Yes, I just.
You can raise your hand so that I can allow you to talk.
Yes.
Yeah. So, sir, particularly, I have one question actually.
Please tell me.
Say, for example, in case of say PCM, we do have a latent heat.
Yes. Yes.
Okay. So, say for example, along with latent heat, if you want to model, say for example, the flow through porous medium, which you have
Yes.
already shown here.
Yes.
Say, I will give another example. For example, heat pipe.
Yes. Yes.
Heat pipe, we have both simultaneously occurring. The flow is going, say steam flow is going upward, where you have a evaporation phase change, and while returning you have a flow through that say mesh or some center material which is a
Yes. Yes. Yes.
weak material. So is it possible to model both at a time?
Yes. So here, when I was showing that shrinkage, so there phase change is also there, which actually tracking the interface between solid and liquid. But it's the V shape, what I showed you, that's a shape between air and liquid, or air and solid actually, air and solid. So that shape is tracked by volume of fluid method, because that is a free. I forgot to mention. So that was tracked through volume of fluid method. So whatever now you were saying,
volume of fluid you have been used. Okay,
yes, yes.
okay.
So now in case of your heat pipe, so as it is a solid and it's a vapor is there, so I will employ volume of fluid method to tag that interface, and obviously I have to use the mass transfer equation, because it's a phase change based from liquid to solid. Okay, so either Lee means if it is condensation, it will be Lee's model. Okay, so that is also there. Whereas if there is some, say for example, you have kept some PCM inside, say in P that we okay. So there also there you can employ this enthalpy method. Okay, but these are all computationally very expensive anyway.
Yeah,
That,
because that is unsteady as well as continuously evolving flows are there. So you'll not
yes,
get
yes,
a steady kind of things there, because every
yes, yes.
time everything is different.
Different. So the computationally it is very challenging. Okay, nowadays people are doing in that way. So coupling between different methods. Okay, like
Yeah.
earlier days UF plus level set people have coupled. Okay, now we are coupling this type of thing. But again, this is a very challenge, because you have to, because it is a numerical program, I can discuss in that sense that you have to stabilize your new model. Okay, your solution
Correct.
rather. Okay.
Correct.
So you see, when seeing the numerical solution, you can actually say whether it is converged or not. Okay. So what happens,
Correct.
as I was telling you during the initiation of this melting, if there is some convergence issue, what will happen? This solution will start oscillating. Okay. So you will
Correct.
always get the oscillating type of profile. But means actually you should not get. There means always temperature should increase, or temperature should not oscillate at about one point. Okay, so if you see that type of problem, that means seeing that result you can understand that there is a problem in there. So then you
Yes,
have
sir.
to
Yes.
state the dimension, when say grid size, or you have to state the time step to capture that. So
Yes. We'll try that, sir. We'll try that.
yes, normally we use adaptive temperature step. Sorry, time
Yeah.
step. Adaptive time step,
That,
depending on that.
yes, sir. Okay. I think
Hello,
there
sir.
is one
Yes,
question
yes, please tell me.
Hello,
from participant.
hello, sir. Good evening, sir.
Good
Nice
evening.
session. Yeah.
Thank you.
Sir, I have a doubt. In order to enhance the thermal conductivity of PCM material, is there any possibility of adding nanoparticles into the PCM for the numerical model simulation purpose?
Nowadays people are using So nowadays people use graphite basically, graphene, or MWCNT. All this thing they are using. Yes, it is very much possible.
How effective is going to show the results, sir?
Okay. If you ask me, I did one experiment, okay, during my masters.
Yes.
I didn't get any result. Why? I'm telling you very frankly, because I have observed that thing. So the problem is that I have mixed the graphene with this PCM, okay, and
Okay.
I uniformly distributed everything, okay, at the starting of my experiment. Now, when I start experiment and when I finish my experiment, I saw that black colored layer is settled on the bottom surface. Okay. And then again I started experiment, and then it didn't actually homogeneously distribute it. So I didn't get the result. So that means the material, the particle, whatever I am mixing, it
Okay.
is actually settling down. Okay.
Okay.
Now, how it can be avoided in that way? So if you use some very small dimension of particles. See, I have conducted these experiments like 2005. Okay, it is 15 years back. Okay.
Sir, but adding nanoparticle in PCM, so we also need to say CFD modeling. So we also need to do take care of that nanoparticles. Say maybe some other techniques we need to add up.
Yes, yes.
numerics.
Yes, yes. So that's what I'm saying. So the normally what people use is that they also functionalize these nanoparticles so that it doesn't settle down nowadays. Okay, one thing. And also these nanoparticles has charges. Okay, on the surface. They also now neutralize that charges by using some coating. So this I have nowadays seen. So now whenever whatever the method you are seeing, if you assume that it is isotropic distribution and porosity as uniformly distributed, then you can take constant porosity, and the way I have showed you in my presentation, you can do it. Means you can use single phase model basically.
Okay. Okay, sir. Thank you so much.
Thank you.
Okay, any other question from participant? Otherwise, we'll wind up. So anyway, thank you very much, Dr.
Thank you
Saha
very
sir.
much. Thank you.
It was a really great session actually. So we got a lot of insight, which
Thank you.
usually not touch upon the latent heat part. We do a lot of heat transfer, all those things, but latent
Yes,
heat, evaporation, that is a really tough part actually.
yes.
Yeah.
All right.
So thank you very much, sir, for
Thank
your
you.
session.
Thank you.
Yes.
Thank you. Thank you. I'm disconnecting the call. Okay.
Yes, yes, sir. Please, sir. Okay, participant, I am sending a feedback link on WhatsApp as well as on your email. Is that okay? I hope so. Okay, thank you very much. See you tomorrow, 9:15. Okay, please check your email. I have already sent on your email. WhatsApp I am doing in 5 minutes. Thank you. Thank you very much.